Hi, welcome back. And so today's lesson we're looking at measuring rate through a change in turbidity, which just like the last lesson is a required practical number 11 if you're on the trilogy course. That's if you're doing them the sciences together, you're not choosing triple sciences. If you're doing triple science, it's the chemistry required practical 5. And what we're going to look at today is we're going to have a look at what turbidity is. We're going to have a look at how we can determine rate based on that, or colour change as well. You can also do it through colour change, and an example method for how to do it. We'll also have a look at some issues with the method and the ways that we can get around those and improve those, because again we should be aware of those. Now, turbidity is a measure of how cloudy a solution is, and the cloudiness is caused by precipitate, and a precipitate, as we talked about before, are suspended undissolved solids in solution. I don't know why it's gone sol.ds. So solid undissolved solids suspended in a solution which prevent light passing through properly. And this is how we would measure turbidity. Normally you get a conical flask here outlined in blue. You put it on a bit of paper with a cross drawn on it, or you can get it with a tile with a cross drawn on it in black marker pen normally, and you start off with two clear liquids which are colourless. So you mix them together and you can see the cross, and gradually as the reaction proceeds it makes this precipitate, and the cross starts to fade and fade and fade until the point you can't see it anymore. At the point you can't see it anymore, you can stop the clock, and that is how you can determine your rate. Obviously, the faster that the cross disappears, the faster the rate of reaction. Next question is what reaction? Okay, so both reactants must be clear solutions, because if they're not clear solutions, then it's going to make it harder to spot the cross already, and it make this method null and void or redundant. And at least one of the products that get made must be an insoluble solid which will precipitate out of solution and obscure your view. You're going to look down the conical flask and time how long it takes for the X to disappear as well. Okay, so it needs to be something that you can do that with, so it can't give off too many toxic products or be too dangerous. And the one we often use in school is we take sodium thiosulfate, hydrochloric acid, and they react together to make sodium chloride, normal table salt, sulfur dioxide, water, and the key one I put in red here is the sulfur. Now the sulfur is an insoluble solid. It's very pale yellow in this solution, but you will see it's quite a vivid yellow when you get solid sulfur, and it will obscure the view of the cross. It will stop the light passing through the solution. So this is a really useful reaction. Slight issue though, sulfur dioxide can, especially for people with asthma, can set off asthma, and when it mixes with water in the air, firstly it will make sulfur trioxide, and then it can go on to make sulfuric acid, and that's probably why it triggers, I would imagine why it triggers asthma, but I'm not entirely sure on that mechanism. So there we go, we've got a conical flask, we've got a sodium thiosulfate and acid in the conical flask, and we've got paper with a cross marked on it in marker pen. Now, hypothesis. Again, I want you to come up with your own hypothesis if you can. So as the concentration of acid increases, the time taken for the cross to vanish. What do you think the hypothesis is? Put it on pause, try and create your own hypothesis. And you should have got the time taken for the cross to vanish decreases. So as the concentration of acid goes up, the time taken for the cross to vanish decreases. So it's faster. This is because, and then you need to explain it using the science about collision theory, which you know now. So give that a go, put the video on pause and describe why the concentration increasing causes the cross to vanish in ever shorter time frames. And you should have something like this, so that when the concentration goes up, there are more acid particles within the same volume of solution, and so that means the collisions are more likely. When collisions are more likely, the rate goes up. Now, the method. Very similar to yesterday's lesson or last lesson, if you're watching this on another day, is you need to describe exactly what you're going to do in nice logical steps. You need to include the variables you're going to change and the variables you're going to keep the same, and what you will measure and how you will measure it, including intervals. So Step 1, measure out 25 centimeters cubed. You could pick 50, you could pick 100, it's just got to be a sensible number. So measure out 25 centimeters cubed of sodium thiosulfate and transfer it into a conical flask. Then measure out 5 centimeters cubed of 0.1 mole hydrochloric acid and add this to the conical flask. Then swirl the mixture once to make sure it's all mixed. You can't obviously keep swirling it because it's got to go down on that cross. If you had a magnetic stirrer, you could use that, and that would be a good way of keeping it stirred. But the problem is with stirring it by hand is you may stir it more or less on different runs, so it could affect your results and make them potentially unfair. So when you place that on the cross, start your timer as quick as possible as well. And when the cross vanishes, when you can no longer see it looking down the top of the reaction mixture, you can stop the timer. Then clean the conical flask and repeat using 0.2, 0.3, etc. concentrations of hydrochloric acid until you reach 1 molar. So that's talking about our range of results. So we're going to do 10 results here, and we're going to go up in 0.1 each time. Nice logical steps. To keep it a fair test, you would use the same strength sodium thiosulfate, the same concentration sodium thiosulfate. We're obviously going to use these volumes. We're going to keep the same person observing the cross, and if you were doing this there's another way you can do this with temperature, and so you might want to also say keep the temperature the same. There are some issues with this method though, and you can probably have a little think of them now. So if you put the video on pause and have a think about what issues you think you might get with the method of looking down the conical flask and looking at the cross and seeing when it disappears. Not thinking about health and safety here, thinking about errors and things that could go wrong. Okay, it can be hard to determine exactly when that cross disappears. When you're looking down on this, and hopefully you'll all get a chance to experience this, when you're looking down at the conical flask into the cross, you'll be like, has it gone? I think it's gone. Oh no, I can actually still see it. It's very, very faint, but I can still see it. When do you decide when that cross is gone? Different people have got eyesight that's going to pick up on this more to a greater or lesser extent. So different people as well are going to say it's going to happen at different times. So there's limited reproducibility of this experiment. Reproducibility means that somebody else can do the experiment and get the same results. To get around this, what we can do is we can use a light meter to record how the light levels fall as the reaction proceeds, and we will have a look at how that setup would be done in a second. But it's more or less exactly the same as the one we've done, except what we're going to do is we're going to clamp the conical flask up, and we're going to have a light meter positioned underneath it, and we don't have to look down the top this time. And here is what that setup looks like. So again, we've got the conical flask. In the blue, we've got our reaction mixture in the conical flask, obviously, and we've clamped the conical flask in place above the ground, or above the bench. We've got our light meter, which often look like, I guess, like a thick pen, a cylindrical object. That's positioned right against the bottom of the conical flask, facing up. So the light that's coming into the conical flask will be absorbed by the precipitate, the sulfur that's been precipitated, and reduce the amount of light that gets to the light meter. The light meter sends its data down to either a display or a laptop or something like that, which will record the data and display it, and you'll see the levels of the light falling. As the levels fall, you can pick what's going to be your end point, so that might be, say, 0.99 as I've got here, and you'll decide that when it falls to 0.99, that's when you're going to stop the timer, and from that you can work out the rate. With that light meter, we can then record the time taken until the light level falls to a certain level, a certain reading. So whatever that reading may be, you may decide that you want absolutely no light at all, which might be difficult if you've got a bright room because some light will still get through. But you might pick a value that's suitable from a preliminary test. So you might do a preliminary test to see what kind of value you might expect to get, and set that as your end point, and then time how long it takes to get to there, say like 0.5 on the readings. And this is going to reduce the errors caused by the difficulty in reading when the cross is vanished. Okay, so it's going to make the experiment more reliable, more accurate, and that's obviously a good thing. Now, a lot of the time in schools, a lot of schools don't have lots and lots of light meters to give to a whole class to do this experiment, which is why it doesn't get done like that. Also, a lot of the time the light meters might need calibration or careful care, and if they don't get those on a regular basis or they're not treated very well, they can lose their accuracy as well. So, summary. Turbidity is how cloudy a solution is, or how much light it allows to pass through. The reaction between sodium thiosulfate and hydrochloric acid makes solid sulfur as a precipitate. Okay, so that's what increases the turbidity of the solution, because we're making solid sulfur. Time taken for the cross to disappear is measuring the formation of a product. It's measuring the formation of sulfur. It's a way of measuring that. And thus the time taken for the cross to disappear is proportional to the rate. The faster the cross disappears, the faster the rate. The slower it takes for the cross to disappear, the slower the rate. Nice and simple. Okay guys, thank you very much for this video. Nice short one today. Please make sure you like and subscribe if you've not already done so, as it does help my channel out. It does help me keep convinced I should keep doing these videos, and I hope you found them useful. And I will see you in the next video, which will hopefully be tomorrow. Okay, bye bye.